Hello, ladies and gentlemen, and welcome to module number 4, Introduction to Inference. Here is where we introduce you to inference. And inference is very basically is taking, we know of a population, we take a random sample, and then we make an inference about the population based on what we learn about the sample. So, for example, you can't possibly ask everybody in the United States what their age is to determine what the mean age of everybody in the U.S. is. And so you take a sample and you ask the sample what their mean age is. And if you took it nice and randomly and not a lot of bias in there, you're going to get an estimator of what the population mean age is. But of course, there are some caveats with it, and that's where we are going to talk about next. So I'm going to talk to you about the introduction, populations versus samples. Remember, population versus sample. It's not just about size. Confidence intervals, because the inference that we make about the population is an estimate, but we could be wrong, and so we need to account for it within confidence intervals. Hypothesis testing, you've probably heard about this, a null hypothesis, the alternative hypothesis, and then merging test and confidence intervals. So without further ado, the goal here is that inference uses the concepts of probability and the tools of data analysis to draw inferences about populations based on the samples. And we get the estimate of uncertainty or the level of confidence associated with the inference. So you might have heard that we are 95% confident about something. We are 90% confident about something. We're 99% confident that the true mean of something based on the sample is this or that. The principles of inference will be illustrated in the setting of estimating the average mean for a characteristic of well-defined population and drawing conclusions about that characteristic. So here we have the youth risk factor behavior surveillance system. Is something that we in epidemiology use a lot. It's something that tells us a lot of information about how youth are doing with regards to risk factors, things like alcohol, smoking, suicide, mental health, things like that. And so it's a survey that the CDC uses every year, and they do this survey on 2.6 million high school students that participated between 1991 and 2013 in more than 1,100 separate surveys. It's still going on today, but the data that we have here are for those. The data set in the Biostat package in R contains responses from 13,583 participants in 2013. And there's 13 variables and then the rows which correspond to the number of responses. Here you see some of the data here. It's a subset of the data, and you see how we have age, we have gender, we have their grade, height and weight. Sometimes we don't have it for everybody. Whether they wore a helmet, whether they're physically active, right? How many days out of the last 7 days were you physically active? Things like that. And so you here have the description of the variables. So population parameter, CDC uses a response of the students to estimate the health behaviors of the target population. So the target population in this case for the 2013 survey is 21.2 million high school students. So here our population is 21.2 million and our sample is 13,572, right? And then we're going to do inferences about the population based on this sample. The mean weight among the 21.2 million youth is an example of a population parameter. And the mean for the sample is known as a point estimate of that population parameter, right? For the population parameter mu, for the point estimate in the sample x bar. Estimating the population mean weight from the sample of these participants is an example of a statistical inference. In nearly all studies, there's one target population and one sample. Suppose a different random sample of the same size were taken from the same population. The sample would consist of different participants, and thus the numerical values of the point estimate could differ from the initial sample. Right? So if I have the big population and I take one sample, and I take another sample, and I take another sample, the mean here might be A, and the mean here might be B, and the mean here might be C, just because, as we said before, there's just this natural variation in things, especially when you take these samples. So understanding the mathematical properties of sampling makes it possible to account for the effect of sampling variability, when making an estimate from a sample. So typically the exact values of the population parameters are unknown. So we typically don't know what 21 point something million children, right, what their mean weight is. And we can observe the effect of sampling variability in an artificial setting where mu, the population parameter, is known. This artificial setting allows us to compare X bar and mu. Suppose our target population consists of those individuals in YRB in the survey, and let the mean weight in the survey be the population parameter, and then we take a sample from that, right? 10 people, calculate the weight. How well does the weight estimate the population parameter? Take many samples to construct a sampling distribution of S. And so you remember the sampling distributions, right? When you flip a coin, right? 5 times is going to be heads, and 5 times is going to be tails. 10 times is going to be heads, and 0 times is going to be tails, or 0 times is going to be heads, and 10 times is going to be tails. If I flip the coin 10 times, it might be 5 and 5. It might be 6 and 5, 6 and 4. It might be 4 and 6. It might be 10 and 0. But as we do this over and over again, most of the time, we're going to get the average, right? 5 and 5. If the coin is fair and it's going to flip on either one and there's a same chance, very rarely will you get 10 in a row of either heads or tails. It's possible, but not very probable. Most of the time, it's going to be around 5 out of 5. And so this is a sampling distribution of a binomial distribution, right? And so it's a nice normal curve. So here you have, using R, using R, this is how we load the library. Then we access our data for the youth risk factor behavior surveillance system. Sample size at 10 out of the 13,000. We set this seed so that we can replicate it. So whatever comes out of this here, the 63 and the 10 over here, with this seed is the randomizer. So when you do this, you can have reproducibility across different samplings. So sample rows, we're going to sample out of the one row, we're going to sample this many in there. And so mean of that sample rows here, because we sample 10, right? Sample size, we sample 10. The mean is 63.639, and the standard deviation is 10. So this is telling us, with just one sample, that the mean was 63.6, and the standard deviation is 10. Right, 10 in either direction. And if we replicate this and change the seed, we might get 64. We might get 62. Very rarely will we get anything way out there, right? This is weight in kilograms. So very rarely will we get this out in the middle of, like, just because very rarely will you have somebody who's very heavy or somebody who's very light. It might be, it's possible, but not very probable. If we do this over and over again, we're going to have the same kind of distribution around the true mean of the population, which at this point is not known. I mean, we could do the 13,000, but for this, we don't know. The histograms plotted in the lab provide an approximate of the theoretical sampling distribution, just like I did right there, for X bar for a specific sample size, in this case 10. Any sample statistic is a random variable because each sample drawn from the population is different. If the data have not been observed, the statistic is simply a function of the same random elements. So in the lab, we saw that the sampling distribution is centered around mu, around the population parameter, and the variability of X bar becomes smaller with larger sample size. So if this were to be 100, this standard deviation would be smaller. So instead of being a broad curve like that, it starts getting like this, like this, like this, as you increase the sample size, to the point that when you sample everybody, when you ask everybody for their weight, it becomes a straight line right on mu. Confidence intervals. A confidence interval gives us the estimate for a population parameter along with a margin of error, right? We're not always going to be right on. Like you saw, sometimes you're going to get 64, sometimes you're going to get 62, sometimes you're going to get 63. And this margin of error allows us to say, you know, how spread is our values. So x bar plus or minus the margin of error is how we express it. To calculate m, the margin of error, we know what is known about the sampling variability of x bar. So mu is a known population mean, sigma is the unknown population standard deviation, n is the number of observations, x bar is the sample means or sample taken, and s is the standard deviation for the sample. The t-distribution is symmetric, bell-shaped, and centered at 0. Sounds familiar? Sounds like the normal, right? That's because the t-distribution, it looks exactly like the normal after an n bigger than 30, more or less. So it's very close to the normal distribution, but has one additional parameter called degrees of freedom. The tails of a t-distribution are thicker than those in a normal distribution. So remember, normal distribution kind of looks like this. The t-distribution has a little bit thicker tails here. There's more values at the ends. When the degrees of freedom is large, greater than 30, the t and z distributions are virtually identical, and degrees of freedom, as you probably guessed now by what I said, has to do with the number in the sample. Degrees of freedom equals n minus 1. So you can see the normal distribution and the t distribution just a little bit thicker over here on the ends, right? With 1 degree of freedom is here, with 2 is here, with 4, with 8, and then normal with 30 or more. 95% confidence interval for the population mean mu is based on a single sample with mean x bar, and this is the formula for the 95% confidence interval. The t is appointed on a t distribution with n minus 1 degrees of freedoms that has 0.975 area to its left and 0.025 area to the right. So it's right here. This is your t value right there that you would plug in into the t star. 97.5% of the area under the curve is to the left, and 5 is to the right. 2.5 is to the right. So if 2.5 is to the right, then the other 2.5 is on the other side, right? And 2.5 and 2.5 is 5, so you have 95%. So you will be 95% confident that the true value is somewhere in here. The function qt identifies a point on a t-distribution with a df degrees of freedom that has area p to the left. So you can do this in R. And so you see this, and you see the degrees of freedom for 9, because we had n equals 10. So then degrees of freedom is equal to 10 minus 1, which is equal to 9. And so you see that the critical t value is 2.262, and then you plug it into your formula, right? 2.262 right here. You have your mean, you have your sample size, standard deviation. This is a mean, this is a standard deviation, this is your sample size, and this is your 95% confidence interval. So this means that we are 95% confident. Pay attention to this. This is a big hint for your midterm and final exam. The way that we express this is by saying we are 95% confident that the true population mean, denoted by mu, we are 95% confident that the true population mean is between 56.46 kilograms and 70.82 kilograms. That is how we read 95% confidence intervals. So if you do it with R, right, you have everything. And in the labs, we'll talk about the t-test, where you do some actual statistical testing. So the general form, in general, this is how you do a confidence interval, right? You can change your degrees. You can change your degrees of freedom. You can change your percent confident if you want to be 99% confident. You know, you can never be absolutely confident of something. You can get out to 99.9%. But if you start doing that, you can imagine that your confidence intervals are really, really wide. But anyway, here you have, if you increase the n to 100, then our critical t value drops. Why is that? Because remember, when you increase the n, you decrease what? You decrease the standard deviation. And it makes sense. Look, if you increase n, then the square root of that number is bigger. And if that number, the denominator is bigger, then this number is smaller. And if that number is smaller, then the margin of error, will be smaller. So if you increase n, margin of error smaller. If X bar could be observed in a repeating sampling, so if we did it over and over and over again, its standard deviation would be approximately this. Right? Thus, the variability of a sample mean decreases as the sample size increases for the same reasons that I just explained. The formula for standard deviation characterizes that behavior more precisely. Okay? Typically, sigma of x is unknown and estimated by standard deviation of x. So then the term Sx over n squared, square root of n, is called the standard error. So we often call this the standard error. Standard deviation is more for population, standard error is more for samples. Confidence level is also called the confidence coefficient. The method illustrated for computing a 95% confidence interval will produce an interval that on average contains the true population mean 95 times out of 100. Or 5 out of 100 times will be incorrect, but of course a data analyst does not know whether a particular interval contains the population mean. We're just confident that it's in there. We don't know for sure that it's in there. I'm 95% sure that it is. I'm not 100% sure that it is. The data used to calculate the confidence interval are from a random sample taken from the target population. So we're assuming, like I said before, that when we sample out of a population, our sample is random. Big hint, again, for your midterm and your final exam. Right? Randomness. While the population mean for the target population is not known, the target population is well defined. There's not people coming in and out of the target population changing its parameters. It's well defined. We know exactly what our target population is. People living in Baltimore City on January 1st, 2020. It's well defined. You know, you don't have people coming in and out, moving in and moving out of the city in one day. Hopefully not a lot. So it's well defined. So hypothesis testing. Here we're going to just give you an introduction to it. So the question is, do Americans tend to be overweight? And so for overweight and obesity, we measure with the BMI. It's an approximate scale used to assess weight status that adjusts for height. You know, if somebody's very if somebody's very tall, then they're probably going to be heavier than if they were short. And so this adjusts for that with the BMI, and this is a formula for BMI. And so the WHO standards for BMI are these. You're underweight if your BMI is below 18.5. You have a healthy weight if it's between 18.5 and 25, more or less. You're overweight if it's over 25, and you're obese if you're over 30. Though I have seen people run marathons and triathlons and they're deemed to be obese because muscle weighs a lot. At least that's my excuse. Anyways, the National Health and Nutrition Examination Survey is another survey, just like the one that we talked about before. And here, the purpose of this one is to assess the health and nutritional status of adults and children. In the U.S., the data set NHANES is in the same data set that you have for the other ones, and it's from 10,000 participants. And so the NHANES SAMP adult data set in the OI Biostat package contains responses for a random sample of participants who were 21 or older. So we will treat NHANES sample adult as our sample and think of the adult participants in NHANES, the entire data set, as a population. Here you just see some of the summary statistics. So we know that our median is 29.10 in the sample, right? Sample. Our median, the interquartile range is right here, and our minimum and maximum. So some people are underweight, some people are morbidly obese. Our mean is in the overweight category. Interquartile range, close to overweight, all the way into obese. So that kind of already answers the question for you, right? And so here you have it displayed graphically. Again, a median right there, the IQR, and some outliers over here. And then here you have it, and there's an outlier over there. So we're going to calculate confidence interval for the population mean. And so here we do it in R. Okay? And we're doing the t-test on that. Confidence level is 0.95. And we're going to create this confidence interval, and we have the confidence interval right there. And we are 95% confident that the population mean is between 18.5 and 24.99. So the population average BMI is well outside the range as defined as normal. I'm sorry, this is not the confidence interval. This is the confidence 27 to 30. So that's pretty high, right? And we already saw it over here. We already saw it right here. It kind of gave us a big hint that it was going to be out there somewhere. So knowing that that's the case, yes, the answer is yes. So a more formal approach to hypothesis testing is having the null and the alternative hypotheses. Two competing population distribution. The null distribution, a usual distribution that has been true in the past, what we know to have been true in the past, and the alternative distribution, the new distribution induced by an intervention or a changing condition. We conclude that the observations come from the null distribution unless the value of an observed statistic is so extreme that it would be unlikely to occur under the null distribution. So these are the steps in hypothesis testing. Formulate null and alternative hypothesis. So usually your null hypothesis is a statement of equality. It's saying that my population weight is the same as my sample weight, or that population A is the same as population B, or that people who take drug X have the same effects as people who take drug Z during clinical trials. And my alternative hypotheses are usually statements of inequality. The mu is actually lower than the sample, or population A is bigger than the sample, not the equal sign, it's actually less than, or X is not the same as Z. Okay? We calculate a test statistic. We specify our significance level, named alpha, so 0.95, usually the usual thing. Calculate a test statistic, calculate the p-value, and state a conclusion in context of the problem. So here you have the null hypothesis posits a distribution for the population that reflects no change from the past. Remember, no change, equality, things are status quo. The alternative hypothesis claims a real difference between the distribution of the observed data and the null hypothesized distribution. So HA is an alternative claim under consideration and is often represented by a range of possible parameter values. So for example, here you have our null is that the mu BMI is equal to 21.07, and our alternative is that it is not 21.7, it's actually bigger. Another alternative is that it is not equal, so it could be bigger or smaller. Depending on the context, is if you want to choose bigger, smaller, or not equal. The significance level can be thought of as a value that quantifies how rare or unlikely an event must be in order to represent the evidence against the null hypothesis. So typically it's 0.05 for 95% confidence, or 99% confidence, 0.01, or some other small value. In the context of decision errors, alpha is the probability of making a type 1 error. The type 1 error is to incorrectly reject the null hypothesis when in fact it is true. It is to say that there is a difference when in fact there is no difference. It's the biggest kind of error you can do. We'll talk about this definition in lab number 4. The test statistic measures the discrepancy between the observed data and what would be expected if the null hypothesis were true. And by the way, this statement right here, big hint for your midterm and final. The test statistic measures the discrepancy between the observed data and what would be expected. Remember, I spoke about this before. Observed minus expected over some sort of standard error is our test statistic. And so here you have it. Observed, we saw this in the sample. We expect this in the population. And this is our standard error, and this is our test statistic. It comes from the t-distribution with n-1 degrees of freedom. What is the probability that we would observe a result as or more extreme than the observed sample value if the null hypothesis is true? That's what the p-value is telling us. Calculate the p-value associated with the test statistic and compare it to the significance level of alpha. A result is considered unusual if the p-value is less than alpha. So if our probability of making a type 1 error is 0.02, and we set our alpha at 0.05, then the result that we just saw, the thing that we just calculated, the p-value that we obtained from that test is significant. And the result is considered unusual. That's what we mean by statistically significant. Our probability of making a type 1 error is very low. We did not make that type 1 error. We did not reject the null when it was true. We went with the alternative. The alternative then has a really good chance of being true. The p-value is not the probability that the null is true, nor is it the probability that the alternative is false. Okay? It's the probability that we reject it when it is true, and not that it is not the probability that it is true. Okay? It's the probability of us making the mistake. For a two-sided alternative that mu does not equal mu of the population, the p-value is the total area from both tails of the t distribution that are beyond the absolute value of the observed statistic. Right? This is our t statistic. If our values are right here, they're significant. If they're in here, they have a good chance of being no different than the null statistic, null hypothesis. The p-value here for a one-sided, for a one-sided alternative, if our value is out here, then it is significant, or the t that we just calculated. Remember, observed as expected over standard error. If it's out here, then it's significant. If it's in here, it's not. The other side to this is the other end, right? If it's over here, if we're looking at something that is less than mu of the population, it would be over here. The smaller the p-value, the stronger the evidence against the null hypothesis. The p-value, if it is as small or smaller than alpha, we reject the null hypothesis, and the result is statistically significant at that alpha level. If the p-value is larger than that, we fail to reject the null hypothesis. Big hint, reject and fail to reject, that's the terminology that we use. The result is not statistically significant at level alpha. In other words, the evidence does not contradict the null hypothesis. Subtle but very important, not rejecting null is not the same as proving that null is true. We simply just don't have enough evidence to say that it is not true. Okay, this really confuses people sometimes. It's like, well, you're not saying that it's equal, you're just saying that we don't have enough evidence to say that it's not equal. State the conclusion in the context of the original problem using language and units of that problem. This is part of the most often omitted by students, but it is important. Right, so here we have the BMI and NHANES, X bar mean of the sample, mu of the population is right there, standard deviation of the sample, n is the number of people in the trial or in the sample. T is X bar minus mu over S squared, and then you have your T value. And so here, then you calculate the P value. It's a very small P value. If this is your T, then it's a small p-value, so your t is out here somewhere at 11. Remember, t is going to be 0, and it goes from positive to negative infinity. So your t is out here, so your critical value is around 2, and you actually got 11. It's way out there, so the probability of the null being, the probability of you rejecting the null is very, very small, so it's statistically significant, so if you reject the null and you go with the alternative. And then this was if you did it yourself as a calculator. If I asked you to do this in pen and paper, this is how you would do it using a calculator. If I asked you to do it by R, then this is how you do it. And this is the output. Your T statistic, your degrees of freedom, n minus 1. Your P value is super small. Alternative hypothesis true mean is greater than 21. Remember, your null is that it's equal. Your alternative is that it's greater. 95% confidence interval is between 28 and infinity. And the mean is 29. So you are 95% confident that the true mean in the population is between 28 and infinity kilograms. That probably has to do with, this infinity probably has to do with that big old outlier that's out there somewhere. So this is how you would do it in R. Two-sided versus one-sided hypothesis test. Two-sided tests are more conservative, as the p-value for a two-sided test is twice that of a one-sided test. We'll talk about how to choose one-sided versus two-sided in lab number 4. But in practice, two-sided tests are usually used, and two-sided tests are expected by most journals and regulatory authorities. Right? You're not looking to see if the average glucose of somebody who takes a medication is lower than something. You're looking to see if it is different than another group. So merging tests and confidence intervals. The relationship between a hypothesis test and the corresponding confidence interval is defined by alpha. Your hypothesis test is that X bar, the average of the sample, is far enough away from a mu to be considered extreme. Your confidence interval is that the mu close enough to X bar to be plausible. In both cases, far enough and close enough are defined by alpha. Right? Again, we talked about this. We talked about far enough out here because our alpha is 0.025 and 0.025 when the alpha is 0.05, right? Far enough or close enough would be in here, and so that's why alpha defines that. If a 95% confidence interval for a population mean does not contain a hypothesis value, then the data contradict the null hypothesis at that significance level, and the implied two-sided alternative is that it's not equal. So we reject the null and we go with the alternative. And that's it. Ladies and gentlemen, if you have any questions, comments, or concerns, put them in the discussion forum. Other than that, thank you very much. After this lecture number 4, we're going to move into the midterm, and I'll have a midterm quick review that I will post the week before the midterm opens. And I will go through lectures 1, 2, 3, and 4 with some key statistical things that you need to understand, those hints that I've been giving along the way. All right? Thank you so much.